and a vice president of the Royal Society. His interests embrace materials chemistry, electrochemistry, especially lithium and sodium batteries, and recent efforts have focused on lithium-rich cathodes for lithium-ion batteries, sodium-ion battery cathodes, and lithium-air battery, as well as solid-state batteries. Today, I believe he will talk about a unified model of oxygen redox and lithium-rich cathodes. Professor Bruce, if you've managed it in just in time, the floor is yours.
Well, thank you very much, John, and welcome. I'm delighted I could join you at last. It's taken most of the meeting up to now to figure out how to connect with you. So it's a great pleasure on your 98th birthday. I'm so sorry we can't all I guess this is the nature of the world. So I chose topic of lithium cathodes, really lithium-rich cathodes, because of course, John, you've a breakthrough with lithium cobalt oxide that led largely to the battery. And also because, of course, Mike is a pioneer of these so-called lithium-rich oxygen redox materials. And so I thought it would be a fitting topic for me to talk a little bit about today. So what I want to look at is, or what we should recognize, I guess, is that there's an insatiable desire always to have more energy density, and a large measure of that, a large barrier to that is the cathode and the ability to store charge in the cathode. And as we know, conventional cathodes are limited to charge storage and employing redox reactions on the transition metal. And of course, the sort of thinking behind these lithium-rich oxygen redox materials is if we could exploit the oxygen redox as well as the transition metal redox, we could increase the capacity of these sorts of materials. So I won't need to dwell, I'm sure, on the introductory parts here, so I'll go through those quite quickly. As we know, there's no such thing as a free lunch, and the possible increase in energy storage that the oxygen redox cathodes might offer us will come at a price, and that price is that we have to figure out some problems that these materials have. And the one that I'm focusing on here especially is the first cycle redox hysteresis. So what you see on the left is the representation of the crystal structure looking along the planes of a typical lithium-rich material. You see it represented up there. It's the lithium-rich NMC. So normally we just have nickel, manganese, and cobalt on the transition metal layers. Inside the square brackets here, we've got extra lithium and these lithium-rich materials, and the transition metals are represented. Sites are represented here. The lithium's in the light spheres. If we use this as a cathode and we charge it up, this is the sort of profile we get, the voltage profile on the first charge, the first redox capacity, and if you charge and then discharge again, you pretty much follow this same line. But if you go further, and you can, and start oxidizing the oxide ions, that's this region here, you have a lot more capacity, but the price you pay is when you discharge again, you come back down at this lower voltage. And so you've lost 1 electron volt of energy, 1 volt, between the charge and the discharge. And although, as I'll show you in a second, you can of course cycle around this region here, you would really like to cycle back and forth along this voltage profile to gain not only the extra capacity of oxygen redox, but also the relatively high voltage, which is high enough to be useful to increase the energy storage, but not so high that it gets into the problems of electrolyte oxidation to too much of an extent. And of course, in subsequent cycles that I've just alluded to, you can cycle this and you can stick around this lower voltage if you accept that. And there's of course issues of voltage fade, etc., and still a hysteresis that you see here, even on second and subsequent cycles. But the main topic for me to focus on today is this loss of voltage on the first cycle. Just in passing, I should say this is really what a hysteresis loop. We use hysteresis for this first cycle voltage loss, but it's not really a hysteresis loop because it's completely irreversible, but it's a terminology, I guess, that we're kind of stuck with. So of course this large change in voltage between charge and discharge in the first cycle signals a change in the structure. Some significant structural rearrangement is taking place. So the probe, the technique that we found, and others too have found particularly useful in trying to understand the nature of oxygen redox, because at the heart of trying to capitalize on this high capacity for practical applications is understanding the fundamental science behind what happens when you oxidize oxide ions and what structural changes are linked to that. So to probe the nature of oxidized oxide ions, RIXS, this resonant inelastic X-ray scattering technique, has been very useful. Just to remind you, applied to oxygen, you excite an electron from the core level, the oxygen 1s level, so it's K edge spectroscopy, to these empty states here, and then you look at the emission from the filled states back into the empty state there. So that's the technique. It's a resonant technique, and we're just going to look at some of these RIXS spectra at key points along the charge-discharge curve for our model compound, this lithium-rich NMC, which is most of what I'll say today is seen in other comparable compounds. So this is just a nice example. So here's a so-called RIXS map before we enter the oxygen redox region. And just to explain these RIXS maps, you have the excitation, different excitation energies along the y-axis, and for each one you have an emission spectrum that's represented as energy loss along here. So this is a sort of whole bunch of emission spectra at different excitation energies. So this gives you this RIXS map at just before the plateau. Here's the situation at the end of oxidation of oxide ions. And the really interesting bit is actually in here. So I'm going to blow this up. And that's this region here. So this is the elastic peak in RIXS. And these progressions here, if you compare them with the progressions for molecular oxygen, you see that they have the same spacing. This is a vibrational spectrum for this oxygen species, captured in the particles, not at the surface and not evolved from the surface. These are oxygens, molecular oxygen, trapped in the particles. You see the same signature for molecular oxygen. Just in passing, to make the point that this does not fit well with an example of a peroxide species. So this is the sort of a vibrational spectrum from peroxide species, which is considerably different from what we observe. So the point here is that we're seeing molecular oxygen trapped within the particles, and when you discharge, you go back to, you lose all this because the oxygen's reduced back down to oxide ions, and you see you've nothing in that region in the spectrum here, and there was nothing in this region before we entered the plateau. So the take-home message is oxidized oxide ions produce molecular oxygen trapped in the particles. We know there's always O2 involved at the surface, but this is O2 trapped within the particles. RIXS is a high vacuum technique, ex situ, so you're not observing any oxygen loss in the electrochemistry. So how is it possible to accommodate molecular oxygen in a structure like this? So here we have the crystal structure again, and here we're looking down onto sort of plan view down the c-axis, and this is the famous honeycomb arrangement, remembering that cobalt, manganese and nickel, the X-ray scatterings are almost identical. So if you forget the distinctions, you see this rather nice honeycomb arrangement that we're familiar with in these lithium-rich compounds. And here's the powder diffraction pattern for this material. And here's the blown up region where we see the superstructure peaks associated with the honeycomb ordering. So if we focus on this honeycomb ordering for a moment and this arrangement here, and then look at what happens when we charge this cathode up, when we extract lithium ions and electrons. We're going to look at three pieces of evidence: the X powder diffraction, which I'll come back to in a moment, lithium-6 NMR, and some STEM data, scanning transmission electron microscopy. So here we're looking along the planes in STEM, and these dumbbells are what you expect to see and what you do see when you have a honeycomb ordering. When you charge up the material, you see that you lose those dumbbells, this smearing out of the light scattering. And the light scattering is from the heavy elements. These are from the transition metal ions. Basically, this is showing us that we're disordering those transition metal ions. So when we extract lithium from the transition metal layers, the transition metal ions disorder mainly in plane. And that's what we see from the PXRD and also from the lithium-6 NMR, where you see that the center of gravity of the lithium-6 NMR signal has changed from the pristine material to the discharged material, indicating that the lithiums do not go back into the same environment. So the honeycomb structure is lost, and you mainly have in-plane disorder. So putting all this together, this is the sort of picture that emerges for oxygen redox, oxidizing oxide ions. You start from the pristine crystal structure here, the blue are the lithium ions, and we just represent all the transition metal ions now with one color for simplicity. We remove lithium ions, oxidize the transition metal ions up here. So we've lost some lithium ions. We charge, we lose most of the rest of the lithium ions at the top of charge. And now we've oxidized these oxide ions, so we've weakened the metal-oxygen bond, and that means it's much easier for these manganese ions to start moving around. And it just requires one hop of each manganese to create this 4-vacancy cluster with these two oxygens, which can covalently bond to form the molecular oxygen. And of course, it's the formation of these covalent bonds which produces a significant energy sink to drive this process. I mean, it's just in passing worth noting that there are two dominantly stable forms of oxygen in nature. Oxide ions, and they're ubiquitous in many, many minerals, and molecular oxygen. And it's not perhaps surprising that when you oxidize oxide ions, molecular oxygen is where oxygen wants to go. And then when you discharge again, you reduce these molecular oxygens back to oxide ions. Crucially, the lithium ions, when they go back into the structure, into the transition metal layers, they do so in different positions, as you saw from the NMR and the pristine. Now they're in these clusters. There's a difference in these crystal structures, and that's reflected in the difference of the voltage of the energy of the beginning of this and the end of discharge. So just to briefly give you a sense of the energetics here, here's some DFT calculations where the gray crosses represent different arrangements of these vacancies created by the loss of lithium from the transition metal layers. The red one is the ground state, it's the pristine material. But what you notice is when you create a vacancy cluster, and this is the simplest one, that allows molecular oxygen, you have a big reduction in the energy. And if you go from this tri-cluster to this 4-cluster, it goes down yet again. So that sort of gives you a sense of the energetics that drives this process. To get a feel for the main factor that's controlling the difference in voltage on charge and discharge, we can look at this somewhat simplified picture. So here's our oxygen sitting between a lithium layer and a transition metal layer with 1 lithium and 2 manganese, just representing the transition metal ions. I know there's a mixture of nickel and cobalt here, but for simplicity. And if we pick out the oxygen 2p state here, that's interacting ionically with lithium, very weak covalent interactions, then these oxygen 2p states will sit at the top of the oxygen valence band. Now, when you charge and discharge, the lithium ions go back into different positions. Now you have oxygens completely surrounded by lithium. And as you'll see from the DFT, we can see from the DFT, this pushes the oxygen 2p states up further. And this is part of what is involved is in single view of what happens when you oxidize oxide ions in these cathode materials, represented. When you oxidize, you lose oxygen from you find transition metal ions diffuse into the empty lithium sites, and you get this so-called densification. And as you do that, of course, you become less oxygen rich, And once you get close to stoichiometric composition, this self-limits. You don't keep going. Whereas in the bulk, when that happens, you're forced, if you create more oxygen, to trap that oxygen in the bulk. So oxygen can explain the evolution at the surface, and oxygen is trapped in the bulk. And my time is almost up, so I just want to, a couple of more slides building on what you've just seen, and this comes to the work that actually is going into the special issue, which I'm delighted to be part of to celebrate John's 98th birthday. And that is that with this unified picture, what controls the balance between oxygen loss from the surface and oxygen, molecular oxygen in the bulk? Well, recognizing that all of these compounds start from the parent Li2NO3, what you see plotted here is the fraction of the capacity due to evolved oxygen from the surface. First of all, here for our Li2NO3, and then if we come down this dotted line, we come to the stoichiometric LiTMO2 composition. So this is going from right to left. This is increasing lithium richness on the transition metal sites, Li2NO3 being one end member, where 100% of the capacity is oxygen loss, the stoichiometric compounds where it's 0. And that would be the dotted line if you simply looked at a statistical average between these two. These lines represent what happens when you dope Li2NO3 with cobalt, nickel, and with nickel and cobalt. And if we focus on the blue one, which is the nickel, you see much reduced oxygen loss in these materials compared with the average. So nickel doping has a very disproportionately favorable ability to suppress oxygen loss. And so to cut to the final message, the reason for that is that in the as prepared material, you have a close to stoichiometric nickel-rich surface layer represented here. If you look at the analysis of the surface versus bulk composition, you see the surface 0.32 nickel, the bulk is 0.2, and you're getting close to stoichiometric quantities of lithium in the material. So the fact that the as-prepared material has a nickel-rich surface, more closer to the stoichiometric composition, sort of self-limits oxygen loss and forces the molecular oxygen to be trapped in the surface. Of course, we know we can coat particles, so there's nothing revolutionary in the idea that surface treatments will do this, but it's the interesting fact that this material sort of has a self-coated effect or self-coating effect. So I think I should end at this point. I want to thank, of course, the people who have done all the work and the funding agencies. Just to say again, it's a great pleasure to take part in this event. Thank you, John, for friendship and support and opportunities in the early part of my career, and to thank everyone else for their attention.
So thank Professor Bruce for your exciting talk. We have collected many questions, so maybe we just ask one or two questions. The first one is, I mean, the molecular oxygen is formed, I mean, on the surface or in the bulk?
It's formed in both the surface and the bulk. So oxidized oxide ions basically go to oxygen, and when they do that on the surface, of course, it's possible for them just to evolve very easily into the electrolyte. But as I mentioned, as that happens, transitional metal ions migrate from the surface into the vacancies created near the surface from the removal of lithium ions, which of course accompany the oxidation of oxide. And that then densifies the near surface region, producing a core shell structure, which limits further oxygen loss. From then on, the system has to accommodate that molecular oxygen in a different way, and it does so by this disordering of the transition metal ions to create these cavities, if you like, inside the particles that will trap the molecular oxygen. And I should say this is a reversible process. You can, as I showed you with the RIXS spectra, you can re-reduce that oxygen back to oxide ions again. And in fact, you can do that on subsequent cycles. So you have oxygen basically everywhere, is I suppose the summary.
Okay, thank you. So the other question is, near the end of the distillation, did you use other technology I mean, to show the oxygen formation.
Yes, I mean, it turns out, and I should say that, of course, there are many other people working in this area that have done made fantastic contributions, and I'm just giving you our perspective on this. It turns out, to have been quite a challenging problem to unravel the mysteries of oxygen redox. I think many people have found this quite a difficult, challenging problem. We have used the problem with techniques such as XPS is that they tend to be very surface dominated. The benefit of RIXS is that it can penetrate about 100 nanometers into a particle, so you can really sample well into the particle. But we have used other techniques, in particular oxygen 17 NMR, which is not an easy technique, but with that, again, it's a bulk average technique, so that's powerful, so you're not surface biased in the analysis. And you can also quantify the amount of oxygen, and the amount of oxygen we quantify from the O17 NMR is in good agreement with the capacity, the so-called reversible capacity from the oxygen redox region.
Okay, thank you. Thanks again, for your exciting talk and your sharing. Thank you.
Thank you very much.